Okay, so I sort of quickly want to talk about flow versus trajectory today. In the previous video, I spoke of these three terms: the vector, field, trajectory, and the ODE. Sort of just wanted to give intuition for that. But today, I just wanted to clear up this confusion that I've had while I was trying to learn this, which is the flow versus the trajectory rate. So to understand the flow, let's first try to revisit what a trajectory is. So let's segregate this here. This is whatever. Let's just start from here. So flow, if you remember, so say at t equals 0, we have a distribution, essentially a collection of noisy image latents, right? Again, try to tie this back to the bigger picture. You pass your image through the variational autoencoder, you get latents, and your um, those latents are um, um, uh, your points here, right? Every latent here corresponds to a point, right? So what I do is You so during the a trajectory is defined for every single point here. So every single latent here. A trajectory is not defined for the entire distribution, but a single vector, a latent vector here, right? So if this is the state of your vector at t equals 0, and this is the state of your vector, and this is the uh, take this vector here, is transformed to this vector here, then your trajectory for that vector um, could be graphed like this if that vector was a 1D element, right? Sorry. Uh, if that vector was a 1D element, you could have a graph like this, right? The trajectory of this vector through time would be like this, right? Again, this is for a single image latent, single vector. Sort of want to um, just reinforce that because that is important, right? Right. So I think that's clear because we've already talked about trajectory before. And again, this is if this graph is for a 1D vector, this was a 4096 dimension vector, you can't possibly graph that, right? So now let's talk about the flow, right? Okay, so a flow is defined like this. It's psi, and you give it your time point and the starting point, right? This is what most resources online say. But the starting point of what, right? Starting point of what? So let's try to understand that. So a flow is a collection of trajectories. I'll try writing that down. Oh god, that's so small, but a collection of trajectories, right? Let me try to sort of, right. So flow is a collection of trajectories, right? Okay, a collection of trajectories. So let us draw the distribution again. You have all of these points, right? All of these points, and each point again corresponds to a vector, and so say we moved from, so this is the state at t equals 0 and at t equals 1, say this is our trajectory, right? Again random points but slightly more oblong manner, right? This is your trajectory at t equals 1, this is your trajectory, sorry, this is your distribution at t equals 1, this is your distribution at t equals 0, right? So a trajectory for this point, like I said, is defined by just the move, just the the change in the state of the single vector across time. But flow wants to talk about the entire distribution, right? It wants to talk about the entire distribution. It is concerned about so it is concerned about every single point in this distribution, right? So that is the main difference between flow and a trajectory. It is a collection of trajectories, right? So I hope that's intuitive now, but again, the next part that again confused me was understanding this mathematically, right? So why do we even do this, right? Um, so if you were to graph this, right, this looks terribly similar to our trajectory graph here, right? But this is the main difference. In trajectory, the y-axis is the vector, the vector that is associated with that specific trajectory. But in flow, this x naught, or you can call it v naught as well, these are the starting points. By starting points, I mean the states of the vectors at t equals zero at t equals zero at every single uh, for every single latent vector here. So if I have say 10 latents here, so this, right? So these are the starting points, and this might move through time like this. This might move through time like this. This might move through time like this, right? This is the flow. This is precisely the flow. So a flow is so if you replicate this graph for all of the points here, you get the flow. Right? Simple as that, right? Now, another thing that sort of confused me. So if that's clear, so we've previously seen here in the ODE that the differentiation of your trajectory will give you the vector field of that vector at that time, right? It's pretty clear, right? I think that's sort of normal. Um, but if I were to differentiate the flow, if I were to differentiate the flow, what will I get? Right, let's try to think through this. So when we differentiate the flow, there's two variables and we try to differentiate across the, the time space, right? So what you should end up with is the uh, the velocities, or rather the changes of the latents at each uh, uh, okay, well, let me try to rephrase this. What you end up with is are the vectors, the direction vectors of the velocity vectors of every single latent here, which is every single point here, right? At this time. So you essentially get the vector field, not for you get the vector field at again, let's go to how the vector field was defined. The vector field is defined okay, I don't think I've written it here, but the vector field is defined for every x and t, right? So you essentially get the vector field, the entire vector field, like all of the vectors together for every point, which is what the vector field is, right? Get the vector field back. Now with here what you got is if you differentiate this, you get the vector field, you get a solution of the vector field at a specific point, if that makes sense. So if this is a vector field and if I were to feed in a specific, so v1, v2, right? feed in V2 and T, um, which is essentially what this is, right? This is the trajectory, right? If you feed in the trajectory here, just a specific vector and a time, you'll get, you won't get a vector field, but you'll get the vector, right? You'll get a singular vector, which corresponds to that latent. But here, when you pass, um, again, this here you're not passing the trajectory, but you're passing the flow, right? Passing the flow, right? Here you're passing the flow. So when you're passing the flow, what you get is the entire vector field itself, this thing, right? You don't get a single vector, but the entire vector field, right? I hope that makes sense because, yeah, so you get the entire vector field at that specific time for every single point here, right? So this is the main difference, right, between um, the trajectory and flow both intuitively and mathematically. And again, I am not sure if I did a great job explaining, but this is how I try to understand this, and if this helps anyone, yeah, yeah, the next video might be about stochastic differential equations. So yeah, yeah.